Hi, nice to meet you all if I haven't already. So I'm Cynthia, I'm a first-year CAPS fellow here, and I'll be telling you guys about a project I just finished up a few months ago with my collaborators, which is about going beyond Fisher forecasting for cosmology. And I just want to say that in this particular project, we focused on cosmology because that's what we do. But the discussion and techniques that we present in this paper are actually broadly applicable to any kind of statistical forecasting. It's not some result that's specific to cosmology. So regardless of what you work on, this is still cool stuff, I think. Okay, so this slide is just an example of recent and current and upcoming ground-based cosmic microwave background experiments, the list of which is not the focus of my talk, but I just wanted to give an example of sort of the nearest future upcoming surveys. So Simon's Observatory is starting to take data, and the next sort of big stage of ground-based CMB experiment will be CMB-S4, which will start taking data in the late 2020s, and this is a collaboration that I'm involved in. So why do we care about forecasting? What is forecasting and why do we care about it? So before you ever build an experiment, you want to be able to estimate how much scientific value you're going to get out of it. So if there's particular science you're trying to do, how well are you going to do it? If you're constraining parameters, how well can you constrain them? So you run forecasts based on the specifications that you expect your experiment to have so that you can quantify how well you think it's going to perform. And it's important to get this kind of right because the outcome of your forecast is going to feed into the design and development of this experiment. There's, sort of a feedback here, right? If there's some particular goal you're trying to accomplish based on some proposed configuration, you'll run a forecast, you'll see how well you're meeting it and whether any specifications of the experimental design need to change. So how do we do forecasting? There's sort of two methods that are the most common. So we need to know what model we're trying to get information about from our data. And we need to have some expectation of what the uncertainties on our measurements are going to be, which is going to depend on things like noise, foregrounds, and all those details that go into how good your data is actually going to be. So one of the most ubiquitous things is this Fisher information matrix, which is n by n matrix, where n is however many parameters are going to be in your model. And this quantifies how much information you expect that you'll be able to get from your data about these parameters. The second common technique is to sample your likelihood more thoroughly with some numerical method like Markov-chain Monte Carlo sampling. So the Fisher matrix is great because its computational cost is very low. I'll show you an example on the next slide, but you basically, usually you're just calculating a handful of derivatives and a covariance matrix, and that's it. Whereas numerical sampling, like with an MCMC, in comparison, is computationally very expensive. And again, why do you care about this? When you're forecasting for an experiment that's still under development, you're going to be running forecasts many, many times for many, many different setups. So anytime you want to consider a different noise or a different foreground model, or you're looking at a different patch of the sky or a different cosmological model, you may want to be testing many variations of these things at once. So it's useful to be able to mass produce your forecasts in a way that is quick and computationally cheap, because it's not like right off the bat you're going to settle on one design for your experiment and run one forecast and be done with it. You're going to be doing this over and over again. Okay, so here's an example of what the Fisher matrix in general. It's going to depend on some derivatives of your likelihood. For a cosmic microwave background experiment in particular, one can show that you can break it down into these parts, which are derivatives of your power spectra and some covariance matrix. And again, these things are not, they're fairly quick to compute. And if you change something, you can just do this over and over pretty efficiently. And once you have the Fisher matrix, if you want the covariance matrix, which actually tells you the error bars that you expect on your parameters, you just invert it. And you can do this analytically. So it's pretty straightforward to work with.
So Cynthia,
Yes.
can you go to the previous one? So you have two covariance matrices, but they're actually different covariance matrices, right? So the first one is the one from the experiment itself, so that comes from some design, I guess.
Right.
And the other one is the actual from that you get.
Yeah, these are different.
Okay.
These are different things.
That's what I wanted.
Yeah, sorry for people that aren't used to looking at these. Yeah, this is the covariance matrix, right, of the things that you're going to observe in the experiment, and this is a different covariance matrix.
And can you tell us a little bit how do you create the first one? I mean, what goes into, how do you figure out what are the inputs for that one? Where do you get them from?
Yeah, so in here, this depends on things like, so your noise levels, for example, are folded into this covariance matrix. So it's going to depend on, in this case, the power spectra that you're measuring, how different spectra at different angular scales are correlated with one another, and the amount of noise with which you expect to measure them. So that precision is contained in this term. The derivatives just tell you if one were to change a parameter slightly, how do the power spectra change as a consequence?
And L1 and L2 are different angular scales.
These are different angular scales, yeah. At some approximation, you can ignore correlations between different L's, but if you want better estimates, different L's amongst the B power spectra can be correlated, and then this covariance matrix gets more complicated and a little more time consuming to compute, but still better than running an MCMC.
So is the idea like you're designing an experiment and it's going to cost more to have lower noise or better detectors or something, but you're trying to strike a balance here, like, well, this is good enough and we're showing that so we can save money.
Right, and sometimes when you're planning these experiments, maybe you have some particular science goal that you're trying to meet. Like, I want to constrain this parameter this well.
Yeah.
And then the question is, okay, what does my experiment need to be able to do in order to measure it that well? Like, how many detectors do we need, or what kind of detectors, or what part of the sky do we need to scan? Do we stare at a small patch for a really long time? Do we do a wider survey because we want more sky but less deep? Yeah, so usually you have some science targets that you're trying to meet, and again, it's sort of a communication between meeting the science goal versus like the limitations of experimentally what can or can't be built and your budget and things like that. Okay, so the Fisher matrix is great, but it has some limitations. It's only a particularly good approximation when your data are actually Gaussian distributed and when the observables that you're measuring depend on the parameters of your model in a linear way. Furthermore, you can calculate a Fisher matrix all you want, but that matrix itself is not going to tell you if it's doing a good job. Right, so you calculate a Fisher matrix, you get some constraints on your parameters, but you don't know if that's a good approximation to the true likelihood or not. So one thing we aimed to diagnose in this project is there a computationally efficient way that you can identify when it's not a good approximation? Because again, of course, you can go run your MCMC and map out a much better estimate of your likelihood, but you don't want to have to do that at every iteration, right? So is there just a quick way where we can say Fisher's doing a good job or it's not doing a good job? Okay, so we've discussed these two things. Oops, sorry. There's a third method, which I want to discuss, which is called the derivative approximation for likelihoods, or DALI for short. And this you can think of as a sort of extension of the Fisher matrix formalism. So where Fisher uses just these first order derivatives that I showed a few slides ago. And the Dolly formalism, you can extend this expansion to higher order derivatives of your observables. And in principle, you can expand this, as far as you want. So if you were to cut it off at lowest order, this first term, this F is the Fisher matrix approximation. But you can now add some additional terms where this G and H are now 3- and 4-dimensional tensors, and they depend on this mu alpha beta is your observables and derivatives with respect to the parameters. So now instead of being first order derivatives, they're second order derivatives. So this increases your computation time a bit because now you're not calculating n first derivatives, you're calculating order n by n second derivatives. But you do get a better approximation to what the likelihood is going to look like. So you can capture some aspects of the posterior that are not Gaussian, which the Fisher matrix cannot do. And as a consequence of that, you can produce constraint contours which are not strictly ellipses. The Fisher approximation will always give you elliptical constraint contours by construction, but that doesn't mean that the actual contours really are elliptical. So some amount of distortion, curving, and banana shape, as I'll call it, can be captured with the Dolly approximation.
What's the space? What is this contour in?
I'll show you in a second. It'll make a lot more sense. One thing I do want to emphasize, though, is where Fisher can be inverted analytically to get a covariance matrix. To get marginalized constraints out of Dolly, you have to do numerical integration, which means that your results can be fussy and depend on the details of that numerical integration. And we did see some issues with this in our work, so we'll come back to this again at the end, but just something to bear in mind. Okay, so what is these contours I'm talking about? These are usually plotted as pairs of parameters and show how well you can expect to be able to constrain them from your data. So this is an example from our paper. It's part of a bigger plot that I'll show you later. But in this case, we're constraining H naught, the Hubble constant, and W is the equation of state parameter for some dark energy model. And there's 3 different forecast results presented here. So purple contours shows what you get from the Fisher matrix. Green shows what you get from the Dolly approximation, and orange is from doing some MCMC sampling over the exact likelihood in this case. So you can see that that one is actually pretty clearly banana shaped, which Fisher doesn't capture at all. And Dolly starts to get there a little bit. So our idea was to utilize the fact that these contours become curved, and you have some points where the curvature of this thing is negative. If you have an ellipse and you trace around it, the curvature of this surface will always be positive everywhere on that ellipse. But if you start deforming it, you're going to start seeing points where the curvature becomes negative. So this is what we leveraged for what we called our curvature test. So we take hypersurfaces where this is constant and compute the curvature on this surface. Now it turned out that computing the curvature on the full n-dimensional thing was computationally, it took a while. So what we ended up doing was taking 2D slices through the surface for every pair of parameter in your model. So if you only have a 2-parameter model, then you're done. But if you have more than that, you slice it every which way that you can for every pair of parameters that you have. And then you have your code make note of the points where the extrinsic curvature of this surface is negative. So you track that. Okay, so coming back to this example, this is the full 3-parameter model that this was part of. So what you're seeing on this figure, the bottom left portion of this triangle is the marginalized contours from these 3 different forecasting methods. The upper right is plotting these cross sections of the likelihood. So these aren't marginalized, these are literally just slicing through the likelihood in different places. And all the red dots are the points at which we detected negative curvature when we calculated this quantity. And we just do this on a grid, some finite grid over the parameter space that you're looking at. And lo and behold, you can see this is the H0 W panel on the upper right. Here it is in the bottom left, that we picked up a lot of points where the curvature was negative, and in fact, this is where the actual likelihood gives a much more banana-shaped constraint than you get from Fisher, and Fisher's not doing a great job. So that's a way that can help. And I should also add that you can calculate these points where the curvature is negative before you ever even do the numerical marginalization for Dolly to get actual constraint contours. All you need is those tensor quantities that I showed some slides back. Once you have those, it's enough to check the curvature. And then if you want to, you can go ahead and get your marginalized Dolly constraints, plot all of this on one figure, look at it by eye, and examine where Fisher seems to not be doing a good job. Okay, this is just another example of a result using CMB data. This is a giant figure. You don't really need to pay attention to the details. In fact, for the CMB, actually, it turned out that Fisher is doing a great job for like pretty much every parameter. We pushed things a little bit in this case because we included neutrino mass. And what starts to happen here is because the fiducial value is kind of close to 0, and obviously physically having a neutrino mass less than 0 does not make sense. So when you're marginalizing these things numerically, you just set a cutoff. You don't sample neutrino masses below 0 because that's not physical. And in that case, like, you do start seeing some deviation from Fisher, and you pick up some negative curvature over here. So just as a word of caution, again, for anyone doing forecasts, if you have, I guess to be more precise, if you have a parameter whose fiducial value is close to some physical cutoff, Fisher is just assuming that this parameter can take values, plus or minus infinity, and there's a chance that you may be underselling your constraining power because the actual marginalized constraints are much smaller than this. And finally, why not just replace Fisher forecasts with Dolly? Well, these convergence issues I mentioned earlier, because you're marginalizing numerically, we saw cases where we would run the exact same setup repeatedly, and we saw enough variation in our results to be worrisome. So they're not necessarily going to be trustworthy. And we also found some toy models where Dolly just like straight up does a worse job than Fisher in approximating the exact likelihood. Like in this right side, exact is orange, and Dolly generates the second peak over here on the right, which has nothing to do with the exact likelihood. So don't just blindly trust it. I guess our recommendation is to use Dolly and this curvature test to diagnose the places where Fisher isn't working, and then if you really need to do your forecast better, then go ahead and use something like MCMC sampling to really map out what things look like. So, okay, I think I went a little over, but thanks.
Do you have any questions for our speaker?
Yeah, so can you go back to the slide where you apart Fisher with, yeah, like that slide. You understand why is Fisher worse than Fisher give the best Fisher? Or give the configuration?
Well, I think some assumptions are no, like for the Kramer-Rao bound to hold, these assumptions that your data are Gaussian and that your parameters are linear have to hold. And if either of those things are broken, then I don't think you can assume that Fisher is going to give the best constraint.
So I understood very little of what you're talking about at this point, but when you were showing the negative curvature that you're trying to calculate, it seemed like there's a one-to-one, like if it's negative curvature, then it is concave, and I saw you said concavity there.
Yeah,
I don't know, could it improve your efficiency if you just showed that it was concave at all, just by kind of like randomly picking points and seeing that there's no way it could be convex? Like, I don't know if you're doing some integration or
instead
some.
of just sampling over like some grid over this.
Well, for like each one of those dots, aren't you calculating what the curvature
You're calculating
is?
the curvature at every point, yeah.
Yeah, and so there's a shape associated with every point there. I was just
Yeah.
wondering if there's some like shortcut where, you know, you kind of sample around and just prove to yourself that it's concave by,
Yeah, I mean, sometimes
One-
it's a little spotty. I don't know if you sampled randomly, if you might get unlucky and just like completely miss all the points that are negative, you know. We didn't play around with it too much because it wasn't, the computation time wasn't so bad that we started looking for ways to cut down on it. So.
okay.
Well, let's thank our speaker again.